Hello, everyone. Welcome to this talk about streamlining large AI models for games with quantization using within Sentis. So, a bit about me. I'm Yusuf. I'm a software engineer at Arm. Arm designs chips, CPUs, GPUs, very prevalent architecture, particularly in mobile. And my job is, as part of the developer advocacy team, is to make sure people can make the most, software engineers can make the most of ARM technologies, particularly focusing on smartphones. So games, AI, these are two things that really push the boundaries of hardware. So when we heard that Unity was developing Sentis, we wanted to make sure that we could get the most out of Sentis with ARM hardware. So this is where the idea of exploring quantization within Sentis comes from. And this whole talk is about the results of that exploration, really. So quantization in Sentis. I hope you all attended the keynote, and you know that Sentis is Unity's new inference engine for AI models. But I really want to discuss sort of AI in games, how it's growing, the problems that this sort of throws up, and then we'll get into using the quantization and how well it performs. So, AI, big topic in the news. It's been finding its way into video games. We've been looking at it, so this is a demo my colleague Koki Mitsunami made. And all these individual rabbits, they're all controlled by a separate smart agent. And the idea was, how many of these agents can we run simultaneously on a Pixel 6? Managed to get about 100. This isn't obviously, so that's some very good performance there, but this isn't the only use case for AI in games. There's things like AI upscaling, segmentation, and everyone's favorite big news topic, large language models. I'm very excited to see what future applications people will find. But the thing is, these models are getting larger, they're getting more capable, they're moving more from the sort of research side to production side as people begin to see the capabilities that they offer. And Unity's clearly taken note, all these new AI tools, Sentis, so we can run all these new models at runtime. But I want to focus on that point there, that they're getting larger and more capable, because this is kind of the cause of a few problems, especially when we're trying to run it on mobile devices. So this is a graph of about 300 of the most recent highly cited papers for AI models and measuring the size of parameters, which can correlate with the amount of compute required, how big the model is effectively. We've got this trend line going up, and it's about a 300 times increase, because this is the log scale. So that's a big increase in the amount of power required for these. Not every type of model is as big as all the 110 billion parameter LLMs that are listed here. Some, like vision models, smart agent models, are smaller, but the trend is the same. They're getting bigger as they get more capable. And yeah, so this is the problem. They're big models, and this causes a hardware constraint problem. We want to run them on a local device, and not every local device is new, the latest hardware. So running it becomes difficult. You've got to fit these large modules into disk. You've then got to upload them somewhere. That's going to cost you bandwidth. If it's like a vision model or you're running at frame rate, you might want to upload it to a GPU to get the acceleration that you need. Well, now you're competing with your graphics pipeline for resources there. And this is always a problem on mobile. So ideally, you could just take one of the smaller less capable models that were somewhere on the graph. But this might not give you the output quality that you want. So what we really want is some smaller models, some faster models, but crucially, maintaining the output quality that you want and need for whatever games you're developing. So there's some existing solutions. You can cloud host these things. This is a popular solution for LLMs, them being particularly large. So that introduces some problems. So if you're doing it frame rate, there's a latency issue. There's this whole infrastructure cost of setting up your servers to run this or paying someone else to do that. And if you're taking things like inputs from webcams or user input, there's a reduced privacy issue, which can be pretty thorny. You could alternatively dig into your sort of ML itself, come up with your own advanced model, but that's a lot of time and investment for training these things. And then there's also some model pruning. You can also try things like model pruning, which, again, make your model smaller, but the results are inconsistent. It's a lot easier to take a model off the shelf from like Hugging Face, find it on some provider somewhere, but these might already be pruned, in which case, oh, spoilers. In which case you can't you might get limited and inconsistent results. So we've been working with Unity to get quantization as a solution to really allow these models to run on more hardware, run more widely, and really get the most out of these new large models that are being developed. So, and quantization, for people who don't know, is simply we take all these floating point 32 values, which is what a model is trained in, what the weights come in. We convert it into some integer value, specifically an 8-bit integer value. So quarter of the bit count, quarter of the size, faster calculations there. So this essentially hits all our key objectives we want. We've now got a smaller model. It will upload faster. The math is faster, so it runs faster. And as we'll see, there's an acceptable quality loss. There's a bit of a quality loss, but it is, there's a comparison slide later on, and you'll see that this is a good trade-off. So been working with Alex to make sure this get this implemented within Sentis, and we've got some good results so far. So a bit of more intuition onto the whole quantization, putting it into int8 things. As I said before, models are trained in floating point 32. They arrive in floating point 32 if you do nothing else. And this is expensive individual calculations. But if we plot the distribution of the weights in a given model, this one's for MobileNet, but many others are like this, you'll see that the weight value is along the bottom. This is a histogram, so amount of weight at that value is the y-axis. Most of the weights fall within this 2 standard deviation range indicated by the bars. We're not using the full range that a float 32 can manage, so we can essentially take that 2 standard deviation range, divide it into bins, assign each bin a integer, and the weights in that bin become that value of integer. So firstly, we can do this to int32. You can see we maintain the distribution. We want to maintain the distribution because this means our output of our model should be approximately equivalent to the output from the FP32 model. But if we only go as far as a 32-bit integer, we don't gain as many performance benefits as we can, right? 32 bits is still 32 bits. So we go further. We go to int8. So splitting this to standard deviation range into 256 bins. The distribution looks approximately similar, very different to the int8 distribution, but one of the important things is that internally, all these models, they don't have this internal sense of scale. So if your input has a certain, say, color value scale, this sort of gets messed around internally in the model. It's not fully aware that 0 to 1 translates to something on a color scale, and you'll get a model, you'll get some integer number out, but as long as it's in the correct scale, you can just rescale it into whatever range you want, back to your color scale, maybe depth or whatever you're trying to do, and your output remains the same. So there's a few gotchas here with quantization. The main one is not all operators can be quantized. So there'll be a bunch of layers, and not all in your model. Not all of them can be quantized, particularly things like the operations that will deliberately squash the range to 0, 1, so things like tanh, sigmoid, or operations that sort of reduce the amount of inputs compared to the amount of outputs, especially in integer calculations, so square root. Fortunately, most of the model time is spent doing things like convolutions, linear layers, all the big calculations where the weights actually get applied. So this is what we've been focusing on with Sentis. So this would be what's called a partial quantization, where you only focus the quantization on the layers that can be quantized. Specifically for this original exploratory work, we've been looking at quantizing convolutions and depth-wise convolutions. So what this looks like in terms of the model is, every time there's a convolution in the model or a depth-wise convolution, we take that, we replace it with this execution graph here, where your values enter in float, they get shifted into the integer range, and the integer range is predetermined by the value of the weights. We form the convolution in the integer space, effectively, and then return back to our floating point 32 afterwards. This is, again, showing we can just rescale between the two, and the values remain the same. So we've been demonstrating this using Midas, which is a depth estimation model, specifically monocular depth. So take a phone camera or a video from that and output some relative depth from that, and we can use that to generate this depth map here. So if I just make that image larger, so that scales the wrong way around. Red is close, blue is far. And we can see that it's focusing nicely on these close chairs here, and the carpet has a smooth gradient as we go back towards the background. And these are in int8, so we can clearly make out what things are. It's not complete, it's not garbled. If we look at sort of things in far, Midas as a model, and we can't beat the model we initially have, doesn't focus on windows. They're transparent. This is a difficult thing to detect, really. So you can see all the depth of the city in the background. We've still got some detail at the front. You can see the chair. You can just about make out the chairs and tables next to the windows, and the TV is there as well. Again, these are int8 results. We can clearly make out where things are. To further this, there is a video. So because we have a depth map, we can draw it on using the depth. So we took this Midas model. We didn't optimize it at all. It's just a model from PyTorch, really. And the model isn't trained on video, so there's nothing in the model itself to enforce temporal consistency, so you get this flickering. But this is a result of the model itself. It's not a result of the quantization. So this isn't a technique to improve your model. This is a technique to take your model and make it execute a lot faster. Again, we can see that it detects the depth of the objects in the room and appropriately colors them. And now, hopefully, we have a live demo of this. So if we could switch to the so this is everyone. This is me, and the depth goes in and out, as with the video. And if Bill would like to come on stage, we can see this in action. Yeah, just walk towards me, and you can make out him coming across. Yeah, do some nice movements. Yep, thank you. So again, this has the flickering because of the model, but we get a nice, stable FPS there. So back to the presentation. Let's sort of dive into the numbers of this. So this is a comparison slide, same picture. One's in int8, one's in FP32. Because the model outputs some sort of some relative value, we have this scale that goes from 0 to 124. That's just how the model works. It's not in any specific unit. You can just about make out there's some error in the background there and some in the foreground, but let's make this a lot easier. Let's really scale up the error just to see where the errors actually are. There's a lot more in the foreground than the background, but the quality loss here is imperceptible, really. So this is a good result. This is what we wanted. In terms of the inference time, this is 54% faster. Remember, this isn't the whole model quantized. This is just part of the model quantized, and we still have to go through all the additional steps of shifting all the values into the quantized int8 frame and then back again. But we still get a 54% faster inference time for the whole pipeline of this. Diving specifically into the convolutions, so this is the speed up of 3 times faster on the convolutions, twice as fast on the depth-wise convolutions. You might think we might be able to get a 4 times speed up, but we've got to also include the additional layers that we added to perform the quantization as we come in. And this sort of messes with the layer fusing that Sentis will do. As you're adding additional layers, it needs to be able to detect those. But if you try and start putting things like layer fusing back in, you can gain additional 11% speed increase on top of that, which is good. And there's the size, the memory reduction. This is an easy calculation because most of the model is weights. If we took all the 32-bit weights, put them into 8 bits, that's just a quarter of the size. So 4 times memory reduction there. Very good. In summary, we've been doing this exploration work to use Sentis and make sure it works more on hardware, and we've sort of achieved our aims here. We've got faster inference time, memory consumption's reduced, bandwidth uploading to a GPU will be reduced. So this is, as a technique, particularly useful on mobile, where the runtime resources are limited, but it's implemented in Sentis, so it's designed to be able to run anywhere. So Sentis was mentioned in the keynote. It's in open beta. We've been using it, not just for this project. We've got some other projects in the pipeline where we're looking at it. Unity's looking at adding quantization for a future release, so you'll be able to get the most of this. I recommend you all try Sentis for your on-device ML needs. There's this QR code links to the general Sentis page, but there'll be a depth estimation sample, and you can learn more about Sentis at the Sentis breakout talk, which Alex and Bill are doing, 1 p.m. stage 4, wherever that is. But yeah, Sentis, good. I've been using it. I recommend it. So thank you all for coming. You've packed out this. Thanks for listening, and we have a Q&A. We've also got Alex here who's been working on a lot of the internal stuff. He can answer some more technical questions on this. Any questions? There's a guy up front here.
Thank you. Thanks for the talk. This is super cool. I have a question about how automated can this be, like in terms of just grabbing a model. Of course, there's some layers that can be compressed, some others cannot. So can this be done almost like automatically? This is like you import the model and then the model checks, oh, I can do this, I can do that, I can do that, and just inserts the layers in there? Or is it something that really requires?
So you need a model that's already quantized, right? Mm-hmm. But quantization is a common sort of optimization technique to get models down this size. So you can take Onyx models and pass it through things like Onyx runtime, and there's a quantization function, quantizes all the models for you, and then you can just, as you would normally with Sentis, drop the model in, start using it.
All right, so then the quantization would be done before you get into the. All right, that's very cool.
Mic work? Hello? Okay, it works. Yeah, I'll add a little bit of detail to that. So there's 2 ways you can do it. So either you do in-training quantization, so you train the model and then you train the weights in training. So that's been more complex. Most framework work most-ish. But the way we do it is you do post-training quantization. So you've given the models already pre-trained. And what the tool is going to do, there's a lot of open tools there from Onyx Runtime that does it, is it will distribute the error distribution across the weights and automatically generate you a quantized model when you can drop. There's a few options there. You can say like, okay, only quantize the convolutions, the matrix multiplications, or propagate it for more layers. So that's like a Python tool. It's pretty easy to use, and do that and then drop it in Unity editor and work.
I think we've got time for a few more questions.
Thank you for the talk. Noob question. So there are operations that can be quantized and some that are not. Could you describe in short variant what is the nature of reason why some operations can't be quantized?
Yeah, so if you look at trigonometric function like cosine and sine, the range is between 0 and 1, right? And it's floating point precision. Like you cannot do that with integers. Like the math precision isn't there. So those specific math functions, like they cannot be quantized. But if you're doing a matrix multiplication, it's just multiply and adds, right? So there's no really any problem with reducing the range of the input and the output. You can just reduce it first, do the math, then upload it afterwards. Same convolution is very similar to matrix multiplication. So essentially, all the layers that just manipulate numbers by doing multiply and adds, they will work. And things that are more complicated, like trigonometric functions or do divisions or things that really need rounding precision, these, they cannot do it.
Thank you.
Maybe one more question.
Thank you. So, good talk. Would you also be supporting other formats like BF16, FP8, other things sort of down the line to enable sort of better better error correction, really?
Yeah. So with bfloat, the problem is that it works on CUDA machines, but DX12 and Vulkan is not in the specs, so it doesn't work. Half point precision, again, the drivers is only you can use like half precision, but that's only a suggestion for the driver. So actually on phones, they actually don't do it, and they run the full math in FP32, so you don't really win quite a lot. You would win if you wouldn't win on like memory saving because the bandwidth is divided by 2. But overall, like the test we did was only giving you like maybe a 20% speed up because the math still needs to happen in FP32, and you only it's only a bandwidth win. So we are looking into it, but it's not that impressive. So it's not necessarily worth the effort. Int8 is good because we it's easy to represent in binary, and you can bit shift to get to 32. There are some intrinsics in newer platform that allows you to do int8 math, but in this case, the phone doesn't support them. So you need to do the math in FP32, but at least you win on the bandwidth. So it's a good in between. That's why we did it.
Thank you.
I think that's time, but if you want to talk to me more, I'll be at the expert bar. I'll have the phone with me, so if you want to see the demo more, you can. Alex will be hanging around as well. There's a Sentis talk later, and there's a Unity AI booth somewhere as well.
Yeah, I'll say that so this demo that you saw, we're going to release it on GitHub soon, maybe today or tomorrow, so you can get your hold and play with it. It won't be the quantized, it'll be the FP32. So you can learn about it. It's going to be a YouTube tutorial. Can explain a little bit how we optimize it. There's more optimization that went in. So yeah, give it a shot. It's called Sentis Sample. Just type that on GitHub and you'll find it.